my longtime friend and collaborator, and also my academic uncle. He's very energetic. He works in representation theory in many topics, and he's very energetic and prolific. And he inspired many mathematicians, including myself. If it were not him, I probably won't continue doing mathematics later on. And he also collaborates with many people. At one time, he was simultaneously collaborating with 14 people. So that makes me wondering that if ever his wife had complained that he had ever had any math time set aside for her, rather than just different topics of mathematics. So recently he was awarded the University of Georgia's Creative Research Award and was presented in front of 90,000 people. Football fans, of course. I only know that field medalist was presented in front of 4,000 or 5,000 audiences. So that was a big honor. And today, please join me to welcome Professor Daniel Nakano from University of Georgia, and who will present the talk on bridging algebra and geometry by cohomology.
Thank you very much, Sanju. Can everyone hear me? Okay. So bridges have a very special meaning in my family. This bridge was constructed in 1937 by my wife's grandfather, and my wife's grandfather owned a construction business in Syracuse, New York. And this bridge spans 1,000 islands, and it allows you access across the St. Lawrence Seaway. It also allows you access across between the United States and Canada. So what I'd like to do in my talk is to show you how cohomology can be used to access the algebraic world and the geometric worlds. But also, I'll show you how you can use cohomology theory to access the quantum world and also the classical world. So the bridges will actually be a common theme throughout this talk. All right, so I'd like to begin my talk by going back to graduate school. This is Graduate Algebra 101. So this is a common problem that you would see in a graduate algebra course. So suppose you have a group, GLN, a group of invertible m by n matrices. So this is acting by conjugation on a set of matrices, but in particular the set of nilpotent matrices. So you can ask yourself, what are the orbits under conjugation? So most of you know, or all of you know, that every nilpotent matrix can be conjugated to an element in Jordan canonical form. So that means that there are only finitely many orbits in this situation. Now I want to make this a little bit more precise because this will motivate a lot of the results of my talk. So the g-orbits are in bijective correspondence with the partitions of n. Okay, so this symbol over here means partition of n. So this is a sequence of positive integers which is decreasing or non-increasing, whose sum is equal to n. And so these parts over here, lambda 1, lambda 2, and so forth, correspond to the Jordan block sizes. Okay? So here's a matrix of Jordan with Jordan blocks of these sizes over here. Okay, so this gives you the correspondence. Now, we can also say that the nilpotent matrices have a topology, a very nice topology, called the Zariski topology. And with the Zariski topology, we're looking at zero sets of polynomials. So nilpotents can be sort of defined by looking at zero sets of polynomials. Okay? And you can define a topology using zero sets. Now, if I take an orbit in GLN, then I can describe the closure in this topology in a very natural way. Okay, so here's the closure of this orbit. And so what I can do is I can look at the transpose partition lambda t, and then look at blocks of size corresponding to that partition and then look at the upper triangular matrices formed by that partition. Then I can saturate it around by the group G, and that describes the closure right on the nose. Okay? And this result down here is due to Crowd. Now, if you're fortunate and you like algebra, you probably took another course in algebra, let's say the Lie algebra course. Now, this slide may look a little bit scary, but I just want to point out that this slide generalizes the setup that we had before. So we start with a complex, simple Lie algebra. Okay, so we could take like SLN, trace 0 n by n matrices, for example. Now, whenever you have a complex, simple Lie algebra, you get a corresponding root system. Okay, so this is types B, A, B, C, D, et cetera, and then you can form a set of simple roots. Now, whenever you have a subset of simple roots, then you can look at what's called a Levy decomposition of the Lie algebra. So, like in the GLN case, we had upper triangular matrices and lower triangular matrices, and we had sort of the block diagonal things. So this generalizes that decomposition. And then we have the Weil group. H will be the Coxeter number. So this is just the number which is associated with the root system. And again, we could talk about nilpotent matrices inside of G. So there's a way to make sense of nilpotents inside of complex semi-simple Lie algebras. And the group acts on the nilpotent matrices by, or nilpotent elements, by the adjoint action, which generalizes conjugation. And again, the number of orbits is finite, just like with the GLN case. And it turns out that these orbits can be classified, and there are different ways to do this. So in the classical case for A, B, C, and D, you can use a partition type classification. And then for the exceptional types, you can use weighted data diagrams or this Fallout-Carter classification. Okay, so now back to graduate school. So we go to Graduate Topology 101. So most people, the way they're introduced to cohomology theory is via their first algebraic topology course. So if you take a topological space, you can associate to this topological space these cohomology groups. This is supposed to be integers over here. And then we learn that cohomology is an invariant of the homotopy type of, let's say, a mountain. And in your topology class, you probably computed the cohomology or the homology of like a sphere or real projective space and lots of different examples, to say the torus. And you're introduced to the idea that cohomology is actually a functor. So the objects are topological spaces. Cohomology sends topological spaces to abelian groups. But it's not just with objects that cohomology relates things to. I mean, if we take a continuous map of topological spaces, then it actually goes to a group homomorphism. So this correspondence is what's called functorial, and it's one of the first examples maybe you've learned of what a functor is. It passes from different worlds, and the correspondence preserves maps in some sense. The nice thing is that cohomology is a convenient way to pass from the geometric world to the algebraic world. So you can create these algebraic invariants which detect things in terms of the structure of manifolds. Okay, so in some ways you're maybe brainwashed in graduate school because cohomology can be used in the other direction too. So what I'd like to do is I'd like to describe how you can take things in an algebraic setting and use cohomology as a bridge to get to the geometric world. All right, so the way we're going to start as follows. So you take a finite dimensional Hopf algebra. So that's sort of a technical condition. And the basic example of a finite dimensional Hopf algebra is the group algebra of a finite group. Okay, so you take the finite group, the basis will be given in terms of the group elements, and the multiplication will be given in terms of the multiplication inside the group. Okay, so this is actually finite dimensional Hopf algebra. Now, you create, so the cohomology for this algebra can be sort of described as follows. So what you do is you look at exact sequences. Okay, so here's the trivial module. Here's the trivial module. You look at exact sequences of modules which sort of fit in between. Okay, so this is an extension or something in X, S of K, K. All right, and then you put a certain equivalence relation on those extensions. Now, it turns out that when you look at these extensions, so these are kind of abstract things, then you can form a ring just by concatenation. So if you take an extension like this, and you take another extension, then the way I multiply these two together is just concatenate. So I stick this K over here with this K over here, and I create this larger extension, and this lies in X to S plus T. Okay, so as you can see, this is actually a graded ring by using this type of multiplication. Now, what we're going to do is we're going to make an assumption on this ring, which is not that stringent of an assumption. We're going to assume that this ring is finitely generated. Okay? So it's a finitely generated K-algebra. So for the case where A is co-commutative, this was proved by Friedlander and Suslin in 1995. But for the case where A is not co-commutative, the problem is still open. Okay? But it's true in many, many cases that the cohomology ring of the finite dimensional operators is a finitely generated ring. Okay, now using the finite generation, we can actually form a certain topological space. So since the even part of this ring, so this is a graded ring, and the multiplication is sort of skewed commutative in some sense. So if we take the even part, then we'll just get a commutative. And so what we can do is we can look at this ring and look at its maximal ideals. So this is finitely generated, so we can look at its maximal ideal spectrum. And that gives us a certain algebraic variety, which we'll call the spectrum of the algebraic variety. So as you see here, we've taken a finite dimensional algebra and we've associated to it a certain affine algebraic variety. Okay, so here's the correspondence here. And let me speak a little bit more about this. So this algebra A is finite dimensional. Okay, so there's really no geometry with something which is finite dimensional. If you take the spec of it, you just get 0. So what the cohomology does, because this cohomology can live at infinitely many degrees, is it really fattens things up. It gives you more information where you can actually define an algebraic variety, define geometry associated to A. Okay. So this is a way to actually give you more information by going to the cohomology. And this spectrum has a lot of rich information that we'll actually see later. Okay, so I sort of gave you a correspondence between the algebra and affine algebraic varieties, but you can also do this with the representation theory too. So if you take a finite dimensional A module, then you could look at extensions of M by itself, and you can look at the action of the cohomology ring on these extensions. So this is given by concatenation also. You just tensor this sequence by M, and then you just concatenate. Okay? And then you can look at the annihilator of this action on here, and then take the quotient. And then take the maximal ideals associated with that, and that'll give you what's called a support variety. So this is the definition of the support variety phenomenon. And notice what happens is that if you take A modules here, then if I associate the support variety to that module, then you get certain conical subvarieties inside the spectrum. So this gives you a way to actually pass between the representation theory and some nice subvarieties inside this big spectrum via A. Okay, so I'm just going to summarize now what we've done. So we start with a finite dimensional algebra, or an algebraic object. And so what we'll see throughout the rest of the talk is that the cohomology can be used as a bridge to introduce some hidden geometric structures. Okay, so these are structures that can be used to say things more about the representation theory. Okay. Structures that you wouldn't just see by looking at models. Also, notice that what I've done is I've reversed the direction of the bridge. So instead of looking at algebraic invariance, I'm now looking at geometric invariance. So I look at representations and I define certain geometric invariance associated with those representations. So the bridge sort of goes back and forth. So what I'd like to do is I'd like to show you how you can apply support varieties to module theory. Okay, so here's a problem. So given a finite dimensional algebra, I can talk about its modules, and I can talk about its indecomposable modules. So indecomposable modules are modules that can't be split further into smaller indecomposable modules. Okay? And so if you take an algebra, a finite dimensional one, then you can express things uniquely up to isomorphism as a direct sum of these indecomposables. So it's very important to know what the indecomposable modules are. Okay. So I want to point out this theorem. So this theorem says something about this correspondence that I set up. So if you take an irreducible conical subvariety of the spectrum, then I can actually find an indecomposable module which realizes this subvariety. So this theorem was due to John Carlson back in the 80s. And from this theorem, you can actually say something about the number of indecomposable modules. So let me just back up for a second. So back in the 50s and 60s, when people were trying to study indecomposable modules, what they would do is they would actually construct them like bare hands. No, they would actually construct an action of A on a vector space and show that they're indecomposable and try to show that they're infinitely many. But what we can do is with this geometric setup, we can actually see why the spectrum will actually detect why there are infinitely many non-isomorphic indecomposable. So the invariant is just the dimension. So if the dimension is bigger than 1 for the spectrum, then you have infinitely many indecomposable modules. So let me show you why that's true. Picture there. So here's a picture of the spectrum. Okay. And so I can take any conical subvariety I want, so why don't I just take this line over here? So by Carlson's realization theorem, what I can do is I can realize this line by the support of some module. And so if the dimension is bigger than 1, then I have infinitely many lines, hence infinitely many indecomposable. So you can use the geometry to actually detect things about the representation here, or the representation type. Okay, so I'd like to sort of step back and give you a little history on the subject. So the subject started in the 60s, and the first sort of main result in the subject was to actually prove that the cohomology ring was finitely generated. So that was proved by Evans and Benkoff in 1961. Then a major advance in the subject was when Quillen was able to actually describe the cohomology ring of Kg. So he gave an actual description of the cohomology ring. So this was in the time where he was making his run towards the field topology, 1974. So later things shifted over to modules. So in 1977, Alpern defined the notion of the complexity of the module. So this is just the rate of growth of the module's minimal projective resolution. And it turns out that the support variety just measures that rate of growth right on the nose. And in the 80s, Carlson and people like Benson and Leonard Scott developed the theory of support varieties for finite groups, which provides the basis for many of the results that we actually studied today. And also in the 80s, Friedlander and Partial and Janssen shifted the focus to other algebras, like the restricted enveloping algebra for Lie algebras. So it was known in these situations for UG, for the group algebra, that the cohomology ring was finitely generated. So it was an open question for many years whether it was finitely generated for an arbitrary finite dimensional co-commutative algebra. So that was settled by Friedlander and Sussman in 1995 in their paper in Inventiones. And then Bendel, Friedlander, and Sussman looked at supports for higher Frobenius kernels. That's an interesting theory because it relates to commuting pairs of Milkov matrices. And then the theory has just sort of spread throughout the last 4 or 5 years. So Friedlander and Petzova have developed a theory in general for arbitrary co-commutative finite dimensional Hopf algebras. So with partial umbrella, we proved what's called the Janssen conjecture that actually gives a calculation of support varieties for certain types of models in the Lie algebra situation. And then we can talk about support varieties for quantum groups, which I'll discuss a little bit later on. And this morning, there's several talks on support varieties for Lie superalgebras. So Katz and Wakimoto define these combinatorial invariants called the defect and atypicality in the Lie superalgebra situation. And it's sort of miraculous that if you apply support varieties for relative cohomology, then you get these invariants right on the base. So the geometry is able to detect these numerical invariants. And then later on, currently Balmer, Blond, Krause, and Solberg have been looking at things from a more abstract axiomatic point of view. Okay, so I want to talk a little bit about Quillen's influence in the subject. The first thing I should say is that you should sort of acknowledge his ideas. And he was a real visionary in the subject. So Quillen won the Fields Medal in 1974. So he won mainly for his work on defining higher algebraic K-theory. So in much of Quillen's work, what you'll find is this theme that he looks at bigger structures, very big structures. And sometimes by looking at bigger structures, you can say something about the smaller structures involved. And so it's very Grothendieck-esque in many ways. And these ideas revolutionize the subject. So instead of looking at small degree cohomology, he would look at the whole thing all at once. So I'd like to kind of attribute, this isn't a quote, so this is a sort of summary of his philosophy. So he would probably say the following. So instead of trying to compute the cohomology degree by degree, instead, why don't we just try to compute it all at once? Okay. So it turns out that this is a very good strategy to use. And the reason why is because the cohomology is really like the coordinate algebra on an algebraic variety. So the dimensions are all interrelated in some sense. So instead of picking things out degree by degree, it's better to look at the whole thing all at once as a graded ring. Okay, and we'll see later that you can make explicit cohomological calculations in this way. So what I'd like to do is to focus my attention next on a very specific situation. So I don't want to talk about every situation involving support varieties, but this really beautiful situation involving quantum groups. So quantum groups, well, it's a misnomer. They're not really groups. They're non-cocommutative Hopf algebras. Okay, and usually when you talk about a quantum group, you're talking about a deformation of the universal enveloping. You form it in a way which it becomes non-cocommutative. And quantum groups were developed in the 1980s. They have lots and lots and lots of applications. So we've seen quantum groups arise in places like algebra, topology, math physics, and analysis. So today I'll show you how quantum groups can be used in the cohomology theory to sort of look at the classical situation. Okay, so G, we're going to start out to be complex, simple Lie algebra. Again, we'll let phi be the root system. And this U of G will just be a universal enveloping algebra. Now, this is just a technical assumption here. So we're going to assume that this L is an odd positive integer, and if we're in type G2, then we're going to assume that 3 does not divide L. This is just to be able to define the quantum group. In addition, we're going to assume that L is not a bad prime for phi. Okay, so a bad prime is just a prime which divides the coefficient of a root when you divide it into, take the sum in terms of simple roots. Okay? And then we're going to let zeta be a primitive all through the unit. Okay, so quantum groups come in different flavors. And so what I'm going to do next is I'm going to define 3 times quantum groups. Actually, I won't define them, but I'll just describe. Okay, so this is a 50-minute talk. So I'm cheating a little bit because I'm not defining them over a generic parameter. So I'm already specialized in this situation. So think of this as like one of those airplane movie talks where it's been edited for time considerations. Okay, so we're going to look at, first of all, the DiConcini quantum group, the DiConcini-Katz quantum group. So this is the deformation, this is like a deformation of the universal development algebra, down here, U of G. Okay. Now, Lustig also defined another quantum group using divided powers, and this again is U of G, but not with a script. So this is like the constant Z form. And then you have this finite dimensional quantum group, which is a small quantum group. Now these are infinite dimensional, and this one's only finite dimensional. And so down here, I'll give you the relations between the two. So if you take the small quantum group, it turns out to be a quotient of this DiConcini-Katz quantum group. Okay? But this small quantum group can also be thought of as a subalgebra inside of this Lustig quantum group. It's actually a normal subalgebra. So what I can do is I can take the quotient of these two. So I can take the Lustig quantum group here, I can quotient it out by the small quantum group, and this is, to me, the most amazing part about this, is you get the ordinary universal enveloping algebra back, non-quantized. Okay? So this already gives you a hint that maybe you can pass from the quantized world to the non-quantized world in a systematic way. Okay, so here's a way that you can systematically go from the quantized situation to the non-quantized situation. So let's assume that I have a module for the Lustig quantum group. Okay, so that's up here. Then I can just take the cohomology of the module because the small quantum group sits inside as a subalgebra. So I can just take the cohomology of that, just restrict the action. And it turns out that the small quantum group acts trivially. And the large Lustig quantum group acts on this. So that means the quotient is going to act on that. So that means that the universal enveloping algebra is going to act on this, which means, because it's locally finite, this is a module for the algebra of G. So in this way, what we do is we get a correspondence between taking modules in a quantized situation over here, applying cohomology, and then we get modules in the classical situation. So this gives a way to go from the quantum world over here to the classical world. Now, let me also say something about these categories. So we're working over the complex numbers, so this category of, let's say, finite dimensional modules is semi-simple. But if you look over here to this category is highly non-semi-simple. So in some ways, if you just work over here, you don't see this category unless you go to the derived level. So it's again hidden, but it becomes more transparent by using cohomology. All right, so what I'd like to present next is, to me, a miraculous calculation. So this is a calculation of the cohomology of the small quantum group when the Coxeter number, or L is bigger than the Coxeter number. So let me say why I think it's an amazing calculation. So this calculation was actually inspired by work in the 80s by Anderson, Janssen, and Friedlander and Marshall. So for restrictively algebra. So this is actually for the quantum situation, and it's due to Ginsburg and Kuhn. So it says the following. So if you take the odd degree cohomology, then it's going to be 0. But if you take the even dimensional cohomology, which is a commutative ring, then you just get the coordinate algebra on the nilpotent. So recall that the cohomology here was defined very abstractly. It was defined just using exact sequences. Right? So how in the heck are you going to be able to sort of understand that? But with this theorem, this is just given in terms of matrices. So you can actually compute this out very, very easily using properties of matrices and get a computation of this very, very abstract object. Remember that H is a constant. So I'd like to illustrate this with an example. So let's say I take 2 by 2 trace 0 matrices. And so I'll show you that if you take the coordinate algebra of nilpotent elements, it's just going to be given by polynomial algebra on 3 generators, factored out by this relation over here. Okay? And once you have this, then you can apply Ginsburg and Kumar and get the dimensions of the cohomology right off the bat. All right, so here we go. So you take your typical 2 by 2 trace 0 matrix here. Okay, so this is a trace 0 matrix. And I just want to know when this matrix is nilpotent. So why don't I just square it? Okay, so I square it, and lo and behold, I get these relations. In order for this matrix to be nilpotent, I need these two relations to be 0, which is precisely the determinant condition. Right? So in order to be nilpotent in SL2, you just need the determinant to be 0. And that gives you this relation over here. Okay, so we've actually computed this out, and then you can apply Ginsburg and Kumar to find the dimensions of the cohomology right off the bat. So this gives you an illustration of what I meant by the Quillen philosophy. It's better to compute everything all at once, and then you can get information about degrees later on. Now, it was an open question for quite a long time, what happens when L is less than or equal to H. So it's been open for maybe 15 years or so. And so in order to describe results in that direction, I have to do the following. I have to talk about stabilizers. Okay, this is just a technical thing. So what this says is the following. So I'm just looking at roots inside of here. Rho is the half sum of positive roots. And I want the inner product of rho with alpha check to be a multiple of L. Okay, so this gives you a subroot system inside the root system. Okay, when L is bigger than H, then this thing is going to be, will be empty. Okay. And then I can do this for any weight. So if I take a weight over here, I can take lambda plus rho alpha check and see whether it's a multiple of L. Okay, I'll use these things in terms of formulating the next results. So recently, Bendel, Kellen, and I answered the question when L is less than H. So we actually describe what the cohomology ring is in that case. So let L be as above. Okay, and what you do is you do the following. You just look at the stabilizer, and you conjugate this to a subset of simple roots generated by J. Okay, this can be done because of our assumptions. Okay? And then you look at the parabolic associated to that, and you can say the following. So the first thing you can say is that the odd degree cohomology is 0, just like Ginsburg-Kumar. Okay? Now, if you're not in type A, when L divides n plus 1, or in E6, when L is not 9, then it turns out you can write the cohomology out fairly nicely. You can write it out in terms of the coordinate algebra on a certain variety. This is what's called orbit space. And then, if you assume further some additional conditions on your orbit, like it's normal, then you can actually identify these two. Okay. So this is the coordinate algebra on this G times Uj, this Richardson orbit over here. Now things get a lot more messy in the type AN in these two cases where L divides n plus 1 and L equals 9. And so I can just show you those for now. So you can compute those out too. So this shows you can get lots and lots of detailed information by using some of these techniques. Now, let me sort of mention a few of the techniques that we used in order to prove this theorem. So one idea we needed the idea of looking at parabolic quantum groups. So it was sort of amazing that this theory was not developed. So we had to be very careful in developing this theory for the parabolics. Another thing we used very strong conditions on line bundle cohomology. So these are results involving complex algebraic geometry, okay, like the Grauer-Riemann-Schneider theorem. We also needed results involving normality of orbit closures, and then finally we used computer calculations quite a bit in order to get this result. Okay, so there was a lot done in order to actually obtain the state. To just generalize things for tomorrow. Okay, so now remember the quantum group is non-co-commutative, so we don't know whether it's finitely generated or not, and you can't just use Friedlander System. So we're actually able to prove the finite generation of the cohomology. And we're actually able to say that if you take an arbitrary module, then it's finitely generated over the cohomology. So that allows us to develop a support variety theory, which turns out to be fairly interesting. Okay, so this actually gives you a computation of support varieties for important classes of modules. So this theorem was inspired by what was called the Johnson conjecture on support varieties for induced modules over G1. Okay, so he made this conjecture in 1987, and Brian Marshall, Dave Bell, and I proved this conjecture in 2002. So this is a generalization of this conjecture to a quantum case. So here we're going to assume that L is bigger than 3, and you have a dominant integral weight. And this is what's called the quantum induced module. Or you can take the quantum viol module, either way. So there's a way to define these modules. Now, these modules have the same character as modules the irreducible modules in characteristic 0. They're given by Viol's character form. Okay, so here's a technical assumption on the prime. So once this condition on the prime is satisfied, then again I can conjugate the stabilizer into a subset generated by simple root J. And then I can just take this saturation of G on Uj and then calculate this variety right on the nose. So remember, these are subvarieties of the no-potent cone, right? And this is just an orbit closure. So this gives you a calculation of these modules inside the no-potent cone. Now, recently, Besnikov looked at tilting modules. So these are modules with a filtration involving these H0s and the duals. And he actually gave a calculation of tilting modules using some really nice geometric constructions. All right, so I'd like to advertise one of my favorite papers in the subject. Okay, so this is a paper that was written in 1986 by Eric Friedlander and Brian Marshall. So if you're interested in getting into this subject, I would highly recommend that you read this paper. Period of invention on this. Now, one of the questions that was given in this paper was the following. Now, this question was not formulated in this way. It was formulated for Frobenius kernels. So I'm just going to translate their formulation into the quantum situation. So it says the following. So suppose I'm given this Richardson orbit G times Uj. So can you find an algebra, a U zeta G algebra A, such that when I plug this algebra into the cohomology, I get the coordinate algebra on this orbit closure. Okay? So here again, we're seeing the bridge between the algebra and the geometry. So here's the geometry over here, given by G times Uj. And it's given here in terms of the coordinate grid. And then here's the algebra over here. So I'm trying to plug in an algebra and then take cohomology and then get to this geometric object on this side. Okay, so as long as you mentioned our collaboration, it goes back many, many years. And a lot of the ways that we collaborate is we meet at conferences, or sometimes we'll be driving through Manhattan and we'll stop in for a couple of days. So this summer we were actually driving through Manhattan, stayed in Sangshu, and this is a result of what happened. So we can actually answer this question to a certain extent. Okay, so let me formulate how we can answer this question. So you take this Richardson orbit OJ, and there's a map from this space, G cross P UJ, to the closure of the orbit. Okay? You just multiply an element of G times UJ, and that's what it is. Okay? There's nothing really hard about that map. So then I can actually construct a finite dimensional U zeta J module for algebra, such that the odd degree cohomology is 0. And when I plug in A to the even dimensional cohomology, I get the coordinate algebra on this variety up here, which turns out to be smooth. Now, if I put additional conditions on this map up here, so if it's a resolution of singularities, okay, and also if this closure here is a normal variety, then I can actually identify the even part with the coordinate algebra on the orbit closure. So this part answers the Friedlander partial question. But normally, this isn't going to happen. Normally, I can only identify things on this, on the thing before, or the smooth space up here instead of the orbit. Okay. And notice that this is a generalization of the Ginzburg-Kumar result, too. So if I take A being the trivial module, you'll see that this just generalizes the Ginzburg-Kumar result, and that was bigger than H. Let me say a little bit more. So in terms of this resolution of singularities, the condition you need is that when you take the element, the orbit element, and you take its centralizer, then you want it to be connected. Okay? And we actually know when that happens. Like in type A, it happens all the time. And then this condition on the orbit closure being normal, so that's actually known for all types except for E6, E7, and E8. Okay, so for all types that's been determined, and for E7 and E8, it's still an open problem for many of the orbits. So let's return back to type A again. So this returns back to graduate algebra 101. So now what can we say? So for GLN, it turns out that you have a resolution of singularities in all cases, and all orbit closures are normal. So then what you can say is that we can find this algebra A, this U zeta G algebra. Again, the odd degree cohomology is 0, and we can identify this and answer Friedlander and partials question for the quantum situation right on the nose. Okay? So to end my talk, I'd like to present some interesting connections. These to me are very interesting facets of this setup. So first of all, again, if I take the algebra, this listed quantum group, then you can apply a spectral sequence argument to get to this statement over here. Okay? So let me explain the statement. So L lambda is a finite dimensional irreducible representation for G, the complex group G. This is the coordinate algebra, and this is the rth graded piece over here. This is the finite dimensional module for G. It's completely reducible, and I can just look at the number of times this appears as a direct sum inside this decomposition. Okay, so this is completely classical. So people like McGovern and my colleague Bill Graham have actually studied this question about composition factor multiplicities. On the other hand, over here, we have cohomology of the quantum group. And this is given in terms of cautionalistic theory. And it turns out this is actually implicit in the work of Broer in 1991. But this makes it much more transparent. In order to get classical multiplicities, you may have to look at certain cautionalistic data in order to get them. Now, the next thing is the Arkhipov-Bezmer-Kalvnikov-Ginsburg paper in 2003. Now, this appeared in JAMS, and they did something quite miraculous with this setup also. So they actually computed the character of the irreducible representations for the quantum group. And the way they did this was they passed to cohomology of the small quantum group. They passed the geometry using the cohomology of the small quantum group. And by doing that, they were able to get into the world of perverse sheaves and looking at the loop Grossmanian and so forth and so on. And they were able to pull all that information back in order to deduce the character formula in that situation. So I think these two things give quite a bit of evidence that there's a lot more out there. There are open questions involving line bundle cohomology in the setting for G modules, which may have a lot of connections in terms of quantum group cohomology. So it would be interesting to actually explore those types of connections. And I think that it would be interesting to really see what one can do by looking at the quantum group situation over here in order to deduce more about this classical situation. Remember, this if you just look at it in and of itself, you don't see the quantum group, but if you pass the cohomology, then you get many more tools in order to study these objects. Okay. Thank you for your time.
Are there any questions or comments? If not, let's thank our speaker again, and I have
I hope you can see the Nakano somewhere there.
This is the evidence.
That's what they do. Thank you all.
Thanks, man.